Hello students, welcome to the class. So today we will be continuing with the structure of atom theory part 6, chapter 2. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. In this lecture, our objective would be, first of all, to understand the important features of the quantum mechanical model of atom. And second is identifying an atomic orbital in terms of quantum number. So we will study every type of quantum number today. If I talk about the subtopics, the first would be quantum mechanical model of atom. So we'll try to understand that what is the base behind this quantum mechanical model. Then we will move on to orbitals and quantum numbers. And lastly, we will practice questions related to these topics. So 2 questions will be there. So we will begin our class, the theory part, with the Schrödinger equation. Okay. So what is Schrödinger equation? Suppose you have an atom or a molecule. So that can be any system, atom, a molecule, or a compound. Now what you want to write the Schrödinger equation for it. How you will write it? So it is written as H psi is equals to E psi. Now everyone knows what is the differentiation of e to the power x. Okay, so what will be the differentiation of e to the power x? If someone asks you, what will be the answer? So what are we doing in this case? So you can write your answer in the chat section, that what is the differentiation of e to the power x. So your exponential, so it will give you e to the power x itself. Okay, so you don't have a change in the function. If you differentiate a exponential function, you will get that function back. Yes, so that will be e to the power x. Now what have you done here? You have taken an operator which is the differentiation operator, d by dx, and you have applied that operator on a function which is e to the power x. After differentiation, you got back e to the power x. So this is a special function in which you get the function itself. Okay. Now, if I ask you, can I write e to the power x as 1 into e to the power x? There is no issue in that. Got it? So what are we doing? We are differentiating e to the power x and we are getting e to the power x back. And we can write e to the power x as 1 into e to the power x. Okay. Now, consider that same situation here also. That H is an operator which is called as the Hamiltonian operator. Now you have to understand it a little swallower. Okay, so you don't have to go much deeper. Just try to understand the basic idea behind that what is the operator and what it does on a function and what does it give. So basically we have a Hamiltonian operator here. Now the beauty of this operator is that if you apply this operator on a wave function which is represented by psi, okay, so it is represented by psi. Now this psi is what? This wave function is basically defining a quantum system. Okay, so that can be electron, a proton, or anyone. So again I am repeating it. So you have an operator similar to the differentiation operator which does something on the function and gives you the output. So here you are taking a wave function which is related to a microscopic particle and you are applying a Hamiltonian operator on it. Then after applying this Hamiltonian operator on this wave function, you will get 2 things. So psi is basically the representation of wave function. Okay. So wave function can be of any form. Suppose you plot the graph of sine x, you will get a wave like thing. Now it is not important that you get a wave, but you can simply take psi as a function, any function. So in this case, suppose you can take it e to the power x, you can take it sine x. So we will not go that much deeper. So what I'm trying to say is that you take a function or a wave function, you apply the Hamiltonian operator on it, and what do you get? You get two things. If your function is good enough, if it is well defined, then you will get two things. First, you will get the function back. Second thing, you will get a value which will be equals to energy. Suppose you have taken e to the power 2x. Okay. Yes, that will be the eigenvalue. So we will not go on to that eigenvalue. So I guess this much is important to understand. Suppose you have taken e to the power 2x. Okay, you have taken e to the power 2x. And then you differentiated this thing. After differentiation, you will get e to the power 2x with a multiple of 2. So this is your what? This is your operator. Okay. This is your operator. This is your function. Again, you are getting back the function multiplied by a factor. Okay, so this is your factor. Now suppose I'm not telling you the actual state of this, say, Hamiltonian function. Suppose our Hamiltonian function is this, operator is this. You applied this on the function. What do you get? You get the function back plus a factor multiplied by it. So this factor 2 will be the energy. Okay, and this psi will be the function. Got it? As simple as that. Now, why it is so? We are getting the energy because Hamiltonian operator represents an operator which helps to calculate the total energy. Okay, so you can understand it. Suppose you are seeing a man who is operating a dumper. Okay, now what he is doing? He is digging a hole. So what is the function of that operator or the driver? That he will dig a hole. As simple as that. So here also the Hamiltonian operator is an operator, and what it will do? It will find the energy of the wave function. Okay, got it? Now in this energy, there will be summation of all the energies that are present at microscopic particles. So this energy will be the summation of all of that. So that will include, first of all, the kinetic energy of all the subatomic particle. So in an atom, you will have two things. So that will be electron and the nuclei. So the kinetic energy of both of them. So first thing. Now what about the potential energy? So there are two types of energy, kinetic and potential. What about the potential energy? So it will counter the attractive potential force between electrons and nuclei. Okay. So this is the first potential energy. And the second potential energy is the repulsive potential force between electron and nuclei, among the electrons and nuclei. So there will be repulsion between the electrons, okay, and there will be repulsion between the nuclei also. So this energy that we got upon operating this Hamiltonian operator on the wave function is the energy that includes all of these types of energy, because all this will be present in a given system. So suppose if you are taking a system that has different type of atoms, so in that system there will be the kinetic energy of the nuclei and the electron, because they both are moving. Second thing, there will be repulsion between electrons. Third thing, if there are two atoms, then there will be repulsion between the nuclei, because nuclei is positively charged, both nuclei. Then there will be attraction between the nuclei and the electron. Okay. So it is very simple. Attractive potential means which is attractive in nature. Suppose the positive and negative charge are attracting each other. Now due to that, the energy that will be developed will be called as the attractive potential. Whereas the electron and electron are repelling each other, or the nuclei or nuclei are repelling each other. So the energy between them will be repulsive energy or the repulsive potential. So what do we get at the end of the equation? We got two things. First, we got the energy, and second, we got the psi. Okay. Yes, that is present. That is stored in the molecule. I'm talking about that only. So if the electron is present and the nucleus is present, so potential energy will be of course stored. Okay. Now moving on further. So we got two things. We got the wave function and we got the energy. Now this wave function has a very important information stored in it. What does it store? It stores the coordinates of the electron. So suppose you want to define the position of a body. You will define the x coordinate, the y coordinate, the z coordinate to define its position. Now in the case of electron, although you cannot determine the exact position, but you can have a probability. Okay. And that probability is defined on the basis of this quantum numbers, which are principal quantum number, azimuthal quantum number, and magnetic quantum number. Now, as I told you, so they arise simply because we got the wave function, and the wave function includes all of this. The wave function which I took earlier was just an example. Okay, so actual wave function has a very complex structure. You don't have to worry about it. You just have to focus that, okay, upon solving the wave function, you will get these values and you pick up these values and use this. That's your point. Now, a very important point to notice here. What is that point? You have an electron that is present in a hydrogen. So, hydrogen has only one electron. You know it very well. So, if you know the wave function of that electron, then that wave function is called as the atomic orbital. Okay. So, we can define atomic orbital in a way that wave function of a hydrogen or a hydrogen-like species with one electron are called as atomic orbitals. Okay. Now remember, students, that your application of this Schrodinger wave equation to multi-electron is very difficult because they have various type of complex forces. So you can't apply this Schrodinger equation onto the multi-electron. Can't apply means what? You can't solve it finally. You can apply it, but after applying those, you will get a very complex equation that will be difficult to solve. So it is very good for one electron system like your hydrogen or hydrogen-like species, but not good for the multi-electron system because it gives us a very complex situation. Okay. Yeah. So what we can say from this 3 points. So first point is very important, that upon solving for a wave function, you will get 3 quantum numbers. First is principal quantum number. So you saw the equation earlier, SI equal to ESI. Now you don't have to worry that how you will solve it because the question will not, of course, not from there. But what you should worry about is that after solving the wave function, what you will get? You will get the value of this 4 quantum number. Now this 4 quantum number acts as a probabilistic coordinate for the electron. Okay. So it will give you an idea where the electron may be present with some error in that. So there can be a possibility that you go and the electron was not present there. Yeah, it is true. So atomic orbital is the reason where the probability of electron is high. We will see that also. Now, is this 3 point clear? Okay. Now moving on further. Now we will try to understand all of this quantum number one by one. That how are they giving the coordinate of the electron? Okay. What does it say? So it has some basic properties you should remember always. First is that it will always be a non-zero positive integer. Okay. So it can be 1, it can be 2, it can be 3. So value of n can be 1, 2, 3. But it can't be a fraction, it can't be negative. Okay, first important point. Now, you must have seen this value of n in the Bose model. So this is that same value. Okay, you don't have to distinguish between these two. So what I am saying is that that this principal quantum number value and the quantum number value which you got in the Bohr's model, that n value, they both are same. These both are same. Now, this n value is important because it tells us about the energy and size of the orbital. So if you go back and remember the equation, you must have seen to find the energy of electron in a given system, it was dependent upon the n. And same was true for the radius also. Did you remember it? Okay, so there was a formula in the Bohr model which helps us to calculate the energy and radii. There you must have seen that energy and radii both are dependent on the n value. Now moving on further. So it helps us to identify the shell. So it's obvious. So we are it is helping up to identify the shell. Why? So if you have K shell, the value will be 1. If you have L shell, 2, M, 3 and N 4. Now you are already aware about this shell thing. We have seen this in your 10th class. Okay. So the value of N increases with this shell count. Now, if you want to calculate the number of orbitals, so I am not talking that much about orbital till now. So we will see a much more depth discussion on it. But before that, there is a formula. So it will be used in the upcoming slides. So that formula tells us that if you have a given value of n, which is principal quantum number, then you can calculate the number of orbital. And it is given by the formula simply n square. Now if I ask you, so this is a very basic question, that what is the number of electron that is related to a given n? What will be the answer? So half of that will be the number of orbital. Okay, so that is certain now. Now next thing, so if you go and look back at the formula for the size, then you must see that the size of the orbital will increase with the value of n, because the size of the radius is increasing in that previous formula. Therefore, the size of the orbital will always also increase. Okay, that means that if the size is increasing, that means electron will be located in a much farther position if it has a greater value of n. So if the electron is present in the first shell, it will be closer to the nucleus. If it is present in the second shell, it will be farther from the nucleus, and it will go farther and farther if it is present in a greater concentric circle. Okay. Now, last, the most important point, that if you increase the value of n, you increase the value of energy. Remember, for the first ground state, what was the value of energy? Okay, in terms of electron volt, what was the value of energy for the first ground state in the case of hydrogen atom? So it was basically minus 13.6 electron volt, the energy of the electron that is present in the first shell. Now if you go further, the energy will become less negative. Okay, that means the energy, so it will be minus 13.6, not plus 13.6. So as you will move away from the nucleus, that means as you keep on increasing the value of n, the value will become less and less negative. That means the energy is increasing slowly. Got it? So we can say that the value of energy increases with n. And what is the reason behind it? If I ask you, what is the physical reason behind it? So you would say that because as the electron is moving away from the nucleus, the attractive force is decreasing. What is the attractive force there? Electrostatic force of attraction. Now it is inversely proportional to the distance. If you are increasing the distance, in turn you are decreasing the attractive force. Therefore, you are increasing the energy. So remember this point always, that if the attractive force, if the number of attractive force is decreasing, the energy will increase, and if the number of repulsive force is increasing, then the energy will also increase. So I guess we have to go to the physics part for that electrostatic thing. Okay. So for now, you can only understand in this way. Suppose two magnets are there. Okay. So take them as charges. So it is not in a literal sense. If you keep them more and more apart, then they will apply less and less force. If you keep them closer, they will quickly stick to each other. Okay. So like that only, if you are keeping the electron and proton far apart, therefore the force of attraction is decreasing. Okay. And as a result, the attractive forces are decreasing, therefore the energy will increase. Got it? Now we will move to the next quantum number, which is Azimuthal quantum number. Now it is also called as the orbital angular momentum or the subsidiary quantum number. Now the important thing about this is it tells us about the three-dimensional shape of the orbital. We will look at it. So now we will focus on the values. Later on we will move to the shapes and all. So what is important? It tells us about the three-dimensional shape of the orbital. Now if you have the value of n, then you can calculate the value of L. Now what is the meaning of this? So basically, for a given shell, the value of n is defined. If you are talking about the first shell, the value of n is 1. Now in that shell, there we will have subshell. What is present in the shell? Subshell is present in the shell. And that is calculated using the value of n, that how many subshells are present. Okay. Suppose you are given that, okay, you have first subshell. Then what are the values of L that are possible? So L will go from 0 to n minus 1. So that will result in only one subshell where the value of L will be 0. Now let us try to understand this with the help of a question. Help of an example. Suppose your value of n is 1. Then the only value of L that is possible will be 0. Okay, we will talk about it, what is subshell and all. Just wait for a while. So you can think of it in a way. Suppose you are carrying a bag. Okay, now that bag will have multiple compartments in it. Now that compartment will have a smaller compartment inside it, and in that you will keep your thing. Okay, now similar to that, electron was also kept in the same way. You have a shell, then you have a subshell, and then you have an orbital, and in that orbital your electron is present. Okay, now how many subshells are present for a given cell? That you can calculate using this formula. Suppose you have the first shell, then what is the number of subshell? It will be equals to the value of n. So if the value of n is 1, there will be only one subshell, and it will have an L value as 0. So two things are there. If you have a shell, which is the first shell, it will have the principal quantum number as 1. Therefore, the number of subshell will be also 1. So the number of subshell is equals to the value of n. Second thing, it will go from 0 to n minus 1. Since we are dealing with this 1 only, therefore only one subshell is possible, and that one subshell will have a L value of 0. Now suppose if you move to n is equals to 2, then what are the values that are possible? So we will again go from 0 to n minus 1. That means, so n is 2, so n minus 1 will be 1. So 0 to 1. Okay, so there can be only two values of L. Again, since n is equals to 2, there are two subshells which are having an L value as 0 and 1. Okay. Now suppose your n is equals to 3. So 3 subshells are there which have the value 0, 1 and 2. Very simple to understand. They are just a thing to remember. If you remember it all, you can solve every question very easily. Okay. Just go through the lectures once again and try to make notes of it. Once you get it, you are good to go. So what I said, that each cell has a subshell which is counted with the value of n, and that subshell will have a certain value of L that will start from 0 to n minus 1. Okay, so you can say that number of subshell is given by the value of n. Now moving on further. Suppose I told you that for the value n, for the value of n as 1, there can be only one subshell whose L value is 0. So similarly, if you have n value as 2, therefore two subshells are possible, 0 and 1. If you have n value as 3, then 3 subshells are possible, which is 0, 1 and 2. I guess it is very easy to understand. There is nothing rocket science behind it, if you are getting this easy point. Okay. Now comes the important part. So you are getting the value of L as 0, 1, 2, 3 and so on. So there is a notation for it related to that. If you have a L value 0, then the notation that will be related to it will be S. Now just try to collect the information that I am trying to give. When I will move to the pictorial representation, you will get a more clear picture there. Okay, so there may be a chance that you will be facing difficulty. But once you complete this lecture, you just keep the informational part with you. Okay. Now, if you have the L value as 1, then the subshell will be P, notation will be P, then for 2, D and so on. Now what we can say? So this is very important, that how do you write the complete subshell notation? Okay. Suppose you are having a subshell which is S and that is present in the first shell. Okay, I told you that if we have the first subshell, then we can have L value as 0 because n is 1. So two things are there, that your subshell is present in the first shell and it is having a value of 0. So 1 and 0 correspond to 1s. Similarly, 2 and 0. So since n value is 2 and for L is equals to 0, the notation is again S, therefore it will be 2s. Then for next, the n value is 2, but the L value is 1. Therefore, the corresponding subshell is P, therefore it can be written as 2P, 3s, 3P, 3D and so on. Okay, just look at it, it's very simple to understand. So what we can see from here, that for the first shell, only one subshell is possible, which is 1s. For the second shell, two subshells are possible, which is 2s and 2p. For the third shell, 3 subshells are possible, 3s, 3p and 3d. Got it? Now moving on to the next quantum number, which is magnetic orbital quantum number. It is denoted by ml. Now this can be a little difficult to get for you, but when you will see the picture of this orientation, you will get a much more clear picture. Okay, so what is written? Just remember it for now, that magnetic quantum number tells us about the spatial orientation of the orbital. Now think of it in a way, suppose you are said that your orbital has a shape of a single line. Okay, so you represent your shape of the orbital with a single line. So I'm taking just an example. But what will be the orientation of this line? If I ask you, then you can say it. 3 ways are possible. It can be oriented along x-axis. So if you have 3 axes, it can be oriented or it can be aligned with the x-axis. Similarly, it can align with the y-axis or it can align with the z-axis. Therefore, 3 orientations are possible. Similarly, our orbitals also have different orientation. It can be along x-axis, it can be between x-axis, it can be along z-axis, and that gives rise to this magnetic quantum number. Now, how many orientations are possible? That will be given by this ml value. Suppose now the shell is defining the subshell, and this subshell will give you the orientation or the orbital. So this oriented shape is called as the orbital. Okay, you can get an idea about this when you will look at the picture. Suppose you have a L value, you know it. Suppose you are talking about the S orbital. S orbital has the L value of 0. Then how many orientations are possible for it? It can be given by 2L plus 1. So 2 into 0 plus 1, that means only one orientation is possible, or only one value of ml is possible. And how we'll get it? To understand that, let us take an example. Suppose if you have L value as 0, then the number of orientation will be 0. Okay. Now, what will be the value of ML? So I have told you that the number of orientation is 0, but we do not know about the value of ML. So value of ML goes from minus L to plus L. So if you take the negative of this 0, that doesn't make a sense. Similarly, if you take the positive of that 0, that also not makes sense. So you only take the value as 0. So ML value is 0. Now you may be facing some difficulty to understand this. For that, let us take one more example. Suppose we have L value as 1. Then what is the number of possible orientations or number of possible orbitals, I would say? So that will be 2L plus 1, which will be 3. Okay, that will be 3. So 2 into 1 plus 1, 3. Now, if I ask you that what are the values of these 3 ML or what are the value of these 3 orientations? So you will go again from minus 1 to plus 1 as the L value is 1. So minus 1 from plus 1 gives you 3 values. Minus 1, 0 and plus 1. So what we can say? That ML value has 3 orientation. Now suppose we take the L value as 2. Then what is the number of orientation? 2L plus 1. So 2 into 2 plus 1, that will give you 5. Now again we will go from minus 2 to plus 2. Minus 2, minus 1, 0, plus 1, plus 2. For 1, it was from minus 1, 0, plus 1. Sorry. So this is all we can say about it. Now this number of orientation is the number of orbital. Okay, number of orientation is the number of orbital. If I talk about the S subshell, it has 1 orientation or 1 orbital possible. For P subshell, 3 orientations or 3 orbitals are possible, and similarly for D we have 5 and F 7 and so on. How do we calculate the value of L? Again, 2L plus 1, a simple formula to calculate that. You can just try it by yourself also. Now let us try to understand what is electron spin quantum number. Now the unique thing about this quantum number is that it is not included in the wave function. I have told you earlier that wave function gives you the value of 3 quantum number: principal quantum number, azimuthal quantum number and magnetic quantum number. But it is not saying anything about this spin quantum number. Okay. So basically, this spin quantum number is associated with the spin of the electron. Now remember students, this spin doesn't mean that your electron is rotating like a top or it is rotating like a planet on its own axis. So this rotation is something which is different. It is intrinsic to it. Now what is the meaning of this intrinsic? Suppose you are looking at a body. You are not allowed to touch it. Okay, you are not allowed to lift it or you are not allowed to weight it. If I ask you what is the mass, you can't tell it because it is intrinsic to that object. It is present inside. Okay. Similarly, this spin also, you can't tell by looking at the electron that what is this spin, because it will not seem rotating like a top or a planet. So it is present like a characteristic of that, say your electron. So if you take a daily life example, if suppose you see a strange person, okay, he is good or bad, you can't understand just by looking at it. Okay. So now suppose if I ask you that is that man tall or short, then you can say it because it is looking in its appearance. So that tallness or the shortness is extrinsic and its character is intrinsic to him. Similarly, your electron spin is intrinsic to the it. Okay. Now since it is having an intrinsic spin, it will have an angular momentum, and that is represented by this spin quantum number. So this is very important to understand. Yeah. So it is not rotating at all. So since it is angular momentum, and angular momentum is a vector quantity, then it can have 2 orientations or 2 sense of rotation. What are those? So that are up spin and down spin. Up spin is denoted by plus half, and the down spin is denoted by the minus half. Yes, it will have it has a magnetic moment, right? It has a magnetic moment. So what we can say? We can say that a electron is there. It will have a spin that will be intrinsic or that will be inside it, and it will have two sense of rotation of that spin. That will be plus half and minus half, denoted by spin up and spin down. Now remember, if you have an orbital, okay, we are talking about the orbital, then it can have maximum of 2 electrons, and those 2 electrons will always have different spins. So suppose you have a orbital, I am representing it by a square, then it can contain maximum of 2 electrons, and they both will have opposite spin. If one is spin up, then the other will be spin down. Now I will try to summarize all of this 4 quantum number one by one. So these are the important points. First is, what does N tells us? It tells us about the energy of the orbital, okay, and also the size of the orbital. If N value is increasing, size will increase and the energy will also increase. Second thing was the L. So L was helping in identifying the shape, okay, and it has given number of orbitals, which is given by 2l plus 1. Okay, so if you follow that, then the P will have 3 orbital, your D will have 5 orbital, your S will have 0 orbital. Now, as L also determines the energy of the orbital in some way, but it is only utilized in the multi-electron system. We will see it why it is utilized in the multi-electron system later on. Just leave this point for today. We will discuss this point in detail in the next class. What does ML was doing? ML was giving orientation. So, for a given value of L, ML, 2L plus 1 values are possible. We have seen it. It means that the number of orbital is equal to the number of ways in which they are oriented. So, I have told you earlier that what is orbital? Orbital is simply the way or the orientation in which your orbital can be oriented. Clear? And lastly, ms was representing the spin of the electron. Now, there is a pictorial representation to represent all of these three. So, what I was telling, I will have a shell. Okay. Inside that shell, we will have subshell like your 2s and 2p. And inside that subshell, we will have orbital. So here we have only one orbital, which is 2s. In this, we have 3 orbitals, 2pz, 2px and 2py. We will talk more about this shape right now. Yeah, this is confusing in a way. So just try to get the formulas and all. Okay. So first of all, you have a shell. Inside that shell, you have a subshell. Inside the subshell, you have an orbital. And inside that orbital, you have an electron. Now we will talk about the orbital in terms of the wave function. So we talked about the wave function earlier. Now we'll try to understand it with the help of orbit and orbital. So basically, orbital was something which was telling about the probability of finding the electron, which was contradicting your Bohr's orbit, which tells us about the exact position. So, since exact position has no real meaning and no existence, it cannot be demonstrated experimentally. Second thing is that, what is atomic orbital? So, it is basically the quantum mechanical aspect that is related to the electron wave function, and it is characterized by 3 quantum number. So if you remember, I have told you that what is atomic orbital? It is the wave function of one electron type species. So you can also say that if the wave function is helping us to characterize n, l and m, therefore atomic orbital is also helping us to say quantify n, l and m, because atomic orbital and wave function in the case of hydrogen atom are same. Hydrogen and hydrogen like atom are same. Okay. What is the third thing? So this is very, very important. There are questions from it, that psi does not have a physical significance. Okay. It is not holding any physical significance. The important part is psi square. So psi square is important. We will look at a graph to understand that. Now, this psi square is basically the probability density. Now, what is probability density? So, compare this density with the density that you see in your daily life. How do you calculate the density? It is mass per unit volume. Okay? Mass per unit volume. Now, if I ask you what will be the mass, you will simply multiply density into volume. Similarly, here, instead of taking that volume, that normal density, here we are taking the probability density, and probability density formula is given by probability by volume. Okay, then what will be the probability? It will be probability density multiplied by the volume. So I told you earlier that probability density is simply psi square. Now don't go into the deep depth part that how this probability density is the psi square. That is a very big thing to consider at this point. Just remember that if you are doing the square of this psi, then you will get the probability density, and if you multiply it by the small volume or the volume, then you will get the probability. Okay. So as I told you, that total probability can be calculated by multiplying psi square with the volume element. So you won't get any numericals on it. Don't worry. But there can be theoretical questions on that, on this statements. That is the reason I am telling you all of this. If you are not able to understand this, just try to learn them at least. Now let us try a question on it. Now questions would be very simple on it if the question is numerical type. But if it is a theoretical type, you must know everything. So this is a numerical type and it's a very easy one. Just look at it. So you have to calculate the total number of orbitals that is associated with the principal quantum number whose n value is 3. How will calculate it? So, if you have a given value of n as 3, then what are the values that are possible for L? It will be 0, 1 and 2. But you have to calculate the total number of orbitals. So, the number of subshells will be how much? It will be equal to the number of shell. So, for the third shell, we will have 3 subshells. 0, 1 and 2. Now what is the number of orbital? So that is simply the number of orientation 12 plus 1. So for each value calculate the number of orbital. 12 plus 1 for 0 will give you 1 orbital. 12 plus 1 for the subshell having the L value as 1 will give you 3 orbital. Whereas the 12 plus 1 value for 2 will give you 5 orbital. If you add all of those, you will get it as 9. But I have told you an easy formula earlier. What was that easy formula? Just remember, just simply take n square and you will get the number of atomic orbital without doing this much fatigue. So simply take n square and that will give you the number of atomic orbital. Now next question. You have to use this SPDF notation and describe the following quantum number. So we have done this 1s, 2s, 3s. You have to do that thing. If n value is 2, L value is 1, what is the notation? N value is 4, L value is 0. What is the notation? And so on. How will solve it? Guess is the easy one. If you are looking at the A1, then in the A, the n value is 2 and the L value is 1. So for L value of 1, the subshell notation is P. Therefore, the subshell notation can be written as 2p. Similarly, for 40 it will be 4s, for 53 it will be 5f, and for 32 it will be 3d. Why? Because for the value of L as 2, it can be taken as the D subshell. For the value of L as 3, it can be taken as the F subshell. Now, I will make you understand that why the psi has no physical significance and psi square has. So this graph can be well used to explain that thing. There are two graphs. One is of psi r versus r and one is of psi square versus r. Now this bunch of graph is for the 1s and the down is for the 2s. Why the psi r is not important or it has no physical significance? Because if you plot the graph, you can see it that if you considered 0 as the nucleus, because 0, here we are moving from left to right, we are moving away from the nucleus. Okay. So if you move close to the nucleus, you will find that the wave function has the highest value. Now this is wrong because there are no electrons that are present at the nucleus. Therefore, this graph has no physical significance because it is intercepting with the nucleus position. That means it is saying that the value of finding the electron is maximum at the nucleus, which is totally wrong. But whereas if you see at this graph, which is present here, there is a small gap always that is maintained up till infinity. And that is the reason it has more physical significance, because it is saying that there will never be electron present at the nucleus, as there will be always a gap in between. It will not meet the nucleus. Now, a very important concept that is to be understood here. If you look here, you can see at two graphs. So I told you that this graph has no physical significance, but remember this graph at least. So the physical significance would be of this graph, which is psi square versus r. Remember, it is for 1s and this is for 2s. If you look at the 1s, it is starting from the top and then it is moving here and it is ending at this point. So after this point, there will be no 1s. But if you look at 2, the 2s is ending here. But before that, there is also a place where the graph is going to 0. And it is within that orbital. Okay. It signifies that orbital is having electron density 0 at this position. And this is called as the node or nodal surface. Okay. So two things I have told you. If you look at these two graphs, then the first orbital, which is 1s, it is ending here. And the 2s is ending here. Okay. So after this distance, there is no 2s orbital. But it has a 0 point for the 2s, which is indicating a node, because here the probability density is 0. Remember that psi square was probability density and it is becoming 0 here. That means there is no probability of finding the electron at this point. And it is called as the node or the nodal surface. Now we will talk about the boundary surface diagram. Now there is an important term in this, which is I guess difficult to understand. If you don't understand it, not a problem to you. But you must at least know that what is the boundary surface diagram for each and every orbital. That is important. How are we getting it? So that is a difficult thing to get because we are not aware of the counter plotting right now. So we will not go on to that. First is, if I talk about what is boundary surface diagram, so basically it is a region where the probability density is constant. Okay. Second thing, in this representation, what you do is you plot a counter surface diagram for the psi square. Okay, so we will not go into how do we plot this. Just remember that how do we get the boundary surface diagram? By plotting a graph for the psi square. And that graph is a counter type of graph, counter plotting. Third thing is that we only take those areas where the probability is 90% or greater than 90%, but it can never be 100 because that will, in that case, it will be deterministic and not probabilistic. So it will be always greater than 90%. That region we will take, and it should be, and it will be obviously less than the 100% point. Now, an important thing, although this psi and psi square, if you compare both of this, then psi has no physical significance, but still, if you plot the counter plot of both of this psi square and psi, you will get the same diagram. Now, what is that diagram? Let us see. So, This diagram will give you the shape of the orbital that we are talking about earlier. Okay, so look at the shape. So this is the boundary surface diagram for 1s and this for 2s. Now remember students, I have told you that you will take only that region where the probability is greater than 90. So see, you can see that dots are also present outside here. So here also there is some probability. So these dots are representing probability. But since it is greater than, it is less than 90 and we enclose only that area which has probability greater than 90. So we are getting this area and not including this one. Okay, similarly for 2s. Now the second one is called as the boundary surface diagram. Okay, and the first one is the what? It is the probability density plot. Here is an important point to remember. If you look at this graph, you can see a region. So basically it is this. In this region, there is a lighter part. Okay, this part is lighter. It is indicating that the probability is going down at this concentric circle. So this is the node that we are talking about. Okay, so 1s has no node, whereas the 2s has one node. So what we can say, if we talk about the 1s orbital, what is the total number of node? It will be given by the formula n minus 1. So 1 minus 1, 0. So of course there are no nodes in this 1s because everywhere the probability is high. Second one, what is the number of radial nodes? So radial nodes are basically these nodes. We'll talk about the angular node also. So radial nodes are these nodes, angular nodes are different. We'll talk about that. So radial node is counted by the formula n minus l minus 1. So for the 1s orbital, n value is 1, l value is 0, and that will give you the number of radial node also as 0. So that can be seen here also. There is no radial node. Again, what is the number of angular node? A very simple formula. Simply take the value of L. So for the s orbital, the value of L is 0. Therefore, angular node is 0. Now let us talk about the 2s orbital. So what will be the case in the in 2s orbital? First, what is the number of node? So that is again n minus 1. N value for the 2s is 2. Therefore, 2 minus 1 will give you 1 node. And what is that node? That node is your radial node. If you calculate the radial node, you will get it as 1. And it has been shown here in this diagram. That lighter region between this darker and this darker region. Again, what is the value of angular node? Very simple. Just take the value of L. So it is again 0. So there will be no angular node in any s orbital. There will be radial node, but there will be no angular node. Next, if you take the p orbital. So this is the shape of p orbital, which is having a dumbbell type of shape. Okay, so this looks like a dumbbell. Okay. What is the number of node? Very simple formula, n minus 1, same thing. That will give you 1. So there will be 1 node in the 2p. What will be the number of radial node? Put the formula, you will get it as 0. Now I am leaving it to you to calculate the number of radial node in 3p. What will be the number of angular node? Again, take the value of L. So for the p orbital, the value of L is 1. There will be 1 angular node. Now this is represented here in this diagram with the help of the square box that you are seeing. Okay. Lastly, our d orbital. So I will try to talk about this d orbital in much more detail in the next class. But we will only focus on now nodes. So what is the total number of nodes? Again, n minus 1, that will give you 2. What is the number of radial node? Take the value of L for D, it will be 1. So 3 minus 2 minus 1, it will be 0. Then the number of angular node will be 2. Because for the d orbital, the value of L is 2. Okay. So this was all for today's lecture. We will meet again in the next lecture with the filling of this atomic orbital. Thank you.